Hey everybody, good morning. I'm Doug Anderson. I am a student at CU. In a prior lifetime, I was a linguist in the Air Force, and I flew on the RC-135 rivet joint and gave up my life in the liberal arts and picked up the engineering side of stuff. So I'm actually a second year here, undergrad at CU. And I've been lucky enough to have a great internship the whole time that I was here at ITS, which is right down the street. I'm going to tell you about some of the work we've been doing at ITS. With spectrum monitoring and specifically LTE. So overall, I'm going to talk about ITS, a little bit of background real quick on it. Spectrum monitoring, our project, why we're doing it. I'm going to talk about bringing the costs down and for these sensors and how a lot of the open hardware and software that you all know and love is playing a big part of that. And then I'm going to introduce something I've been working on called the LTE Trigger. So super quick, ITS, for those that you don't know, is a national research laboratory, part of the National Telecommunications and Information Administration. We share a laboratory right down the road with NIST and NOAA. And we do a lot of research that affects spectrum policy. We work with other agencies that have spectrum issues. It's kind of a spectrum hitman for the government, I guess. That's probably a bad analogy. So somebody comes to us with an issue about spectrum, we have the tools. And one of the tools that we traditionally would use is something like this, the RSMS, the Radio Spectrum Measurement System. It's a truck filled with a bunch of lab equipment. It's RF shielded, 60 dB of attenuation inside, 3 masts. And so when we have a specific question to work on, we roll this out. And the way that we generally would use something like this is we would prepare the equipment for the specific task, drive the truck somewhere, park it in a parking lot, put something up on the mast, measure for a week or so, drive the truck back, download the data, and spend the next 6 months or so analyzing the data and writing reports. With equipment like this and techniques like this, it's really important that we know the question in advance, because you don't just hop in the truck and go out for a cruise to see what's going on in the spectrum. So some of the problems that we currently know that we're working on with this kind of stuff is radar like this, which is a radar used by the Navy. I think it's spin 43, is that right? It's in 3.5 gigs. And almost always, I don't know if standard operating procedure is to ride the radar, but almost every picture I found, actually there's somebody riding it. Sounds cool. I'm Air Force, I don't know about the Navy guys. This radar is almost always on ships. Ships are almost always in the water. 3.5 gig is a nice bit of spectrum for communication sensors like LTE, and LTE users are usually not in the water. And so the question is there some way that we can share? Some way we can use both at the same time? Another example, this is a satellite downlink, Earth station. This is actually part of something that we use at ITS out at Table Mountain here in Boulder. Let's pretend it's a NOAA satellite. So trying to get the downlink for, try to get the satellite downlink for weather satellites, like the kind that are used by, that you can read with GR-NOAA. In a situation like this, it also sits in very nice spectrum for communication sensors, and for communication like LTE. And there are only a few of them, and they're in some pretty remote places. I think there's one in Barrow, Alaska, and they're all over the place. But both of these technologies are very important. You don't want to mess with them. But again, is there some way that we can use both at the same time? And the question is, right now, definitely not. That's the guy that says, hello, right? Because right now, as you've all seen that spectrum chart, a million times, so I didn't want to put it on here again. Spectrum in the US is located by frequency only, right? And so you're going to have this, and then you have really sad meteorologists that can't predict the weather. So the solution to this is something you all know about, so I don't want to labor on it, but it's spectrum sharing, right? So we want to split up spectrum not only in frequency, but in time and space. So thank you, loud cell phone man, you got to stay out of the exclusion zone, right? And so these incumbent systems definitely deserve to be protected, and policymakers know that spectrum sharing is the way to go, and they want to move on it, but ITS, who does a lot of research trying to provide data for policymakers, doesn't provide the kind of data that makes making these policies easy. So stick with a meteorological theme for a second. Maps like this, even though weathermen meteorologists have maps like this, still they fail to predict the weather quite often, right? But this map has a lot going for it, I think. It's got a lot of information about here and there. It's got information over time, so it's pretty easy to see trends. You know, if you look at it, you can see what's going to happen next, maybe, in the short term. ITS and the truck that I showed you, RSMS, the way that we work, where we drive the trucks to one place, we lose a lot of SA. You know, we don't have this this kind of picture. In other words, if ITS were responsible for weather maps, it would look like this, where the truck is parked there, and you get a short duration of what the spectrum looks like. But everywhere else, you don't know. And it's this kind of problem where policymakers really want to move on this kind of spectrum sharing stuff, but this is the kind of data that we're able to provide them. They're not going to make good decisions, right? It's for this exact reason that the spectrum monitoring project was started at ITS, and I'll tell you about some of the stuff we've been working on. So, ITS, in collaboration with the Communications Technology Lab out of NIST, together we make the Center for Advanced Communications, CAC. And one of the things we're trying to do to create this nice weather map of spectrum in a way is first we need to aggregate data. We need to take sensors and put them out and leave them there so that we don't need to go and then come back and analyze data. We want the data to come to us. And so one of the things that we've created, and this is live now, we actually took it public at ICER a few months ago, is the Measured Spectrum Occupancy Database. And we have just a few sensors up on it now. So around the coast, you can see some actual and synthesized radar sensors. And toward the center here in Boulder and in a lab in Gaithersburg, we have some communication sensors just sitting on lab benches right now. But these sensors are there continuously. They have a continuous connection to the database. A radar sensor you don't need to see data streaming all the time, but it could post data. A communication sensor might be more interesting to see the data live, like a live stream. So we can actually do that as well. We can create a socket connection and stream data. And I just got lazy with the screenshots. You can completely ignore this garbage down in the bottom left. Actually, it's supposed to look like on the right. So this is what it would look like if you selected, back real quick, if you selected the band that this comm sensor supports and is looking at, you'd see something like on the right side there where this is looking at 751 downlink, and this is just from a antenna on the roof of our lab. and the data comes in as just occupancy data. And so we can see this fine-grained data in real time. Clicking other ways, we can see occupancy measurements over a week, a month, whatever fits the kind of data that you're looking at. And it's this kind of idea that we think will help making decisions about how to best make spectrum sharing a thing possible. So let's see. So yeah, it's a great tool for visualization, and an important part of it is that we have a decent amount of sensors sending data to it, right? And I showed you the spectrum analyzers and the lab-grade equipment that we tend to use. That's not going to scale at all. So one of the things that we've had to do that's really new is to break into this kind of area that we're working with here, lower cost hardware, and open source software. And as we do that, we want to maintain the high quality that we tend to have already. And so one of the big parts of the project is testing and characterization of the different sensors before we put them out in the field. And this is what I meant by field ready, not necessarily weatherproofing or anything like that, but what we want to do is we want to fully characterize the sensors and the software that we're going to run on them before we put it in the field, because if you fly an engineer to the coast to set up some piece of hardware, start it running software, and then you fly back to Boulder and you decide that something's not quite right and you can't trust the data, right? You have to fly back and fix it. You don't want to do that. So when we say field ready, what we want to do is we want to really fully characterize these sensors so that we can trust the data that they give us. And so some of the things that we do are obviously power calibrations. We do amplitude, accuracy, frequency, stability, 1 dB compression point, DANL, the displayed average noise level, and a whole suite of standardized tests. And the thing that we're trying to do is to run these standardized tests over a large range from spectrum analyzers, kind of the gold standard, down to the lower cost sensors, lowest cost sensors that we want to try to put out there. And the idea is to kind of make kind of a cost versus capability matrix where when we have some need to put a sensor out in the field, we can go to it and we choose the best sensor for that job at the lowest price. So this is the actual sensor that was running the comm sensor spectrum that I showed a little bit ago. And we're a very small team, and so this leads to some idiosyncrasies as we work through the issues of going from the RSMS style lab grade equipment down to the cheaper sensors. So for example, we've got a B200 here in the box, and we've gone from a laptop or something like that down to a mini ITX board computer with an i7 on it. That's about $600 to put together, and that'll all fit in a 6-inch tall enclosure. But the idiosyncrasy here is that we still want to protect the front end and be sure we can trust the data coming from it. And so we've still got this kind of giant pre-selector in front of it. That's probably got cavity filters, and I don't think this one does, but we often have noise filter, stuff like that, noise diodes. And those together are a lot more expensive than the actual sensors that they're protecting. So that's, that's a bit of an idiosyncrasy, and we're working on that as well. Actually, this fall and this spring, we're working with a group of CU students that are going to try to take this and miniaturize that as well and bring that cost down so that we can, like I said, so we can trust the data that comes back from these sensors we're putting out. This is probably a good time as any to bring up privacy at any time that we're talking about sending and storing spectrum data in a database. It's something that we should all talk about. And so on the next slide, I'm going to mention briefly that we do talk about this all the time at ITS, and I'll tell you what we do and don't do with IQ data. So this would be a block diagram of, say, the B200 running a gunner radio flow graph, and it's pretty standard, power spectrum on the top here, and that would be sent to the measured spectrum occupancy database, MSOD. But once that data is decimated, you lose a lot of information, right? There's a lot of good stuff in the IQ, and you don't just want to throw that away. But you don't want to store it in the database, and you don't want to send it over the wire. So one of the ways that we're trying to deal with that and try to get the most out of the data safely is to do analysis at the sensor, basically as a gunner radio out-of-tree module type of block where you can just plug it in, throw the IQ into it, and see if we can find anything interesting. And then if it does find something interesting, it can do an asynchronous event message to MSOD, kind of say, hey, check this out, this is noteworthy. So a couple examples of what might be an interesting event. Say in a comm sensor, if we were to put it out to monitor an LTE entrant, if the entrant was an uplink, then obviously you would want to try and see if you can detect an in-band UE. And if the entrant is a downlink, clearly you would want to say, I wonder if there's an eNode B in band. And for anybody who's ever done any LTE work, which one's easier, uplink or downlink detection? Downlink by far, so guess which one I started with? Yeah. So this is a GRLTE Trigger. And it's not a very, it's named GRLT Trigger because it's supposed to trigger an event to MSOD when it runs against LTE. And this is an example of it running on the RTL SDR in my office with the stock antenna. So what it is a wrapper around SRS LTE. SRS LTE is a pretty lightweight C library for doing LTE. And so I've kind of wrapped those function calls and so that we can throw in data and we get that nice abstraction. Like I said, the analysis blocks are just out of tree modules, so we can do, put in a file source or an RTL SDR or anything. That's what I like about the gunner radio block. At the same time, I don't necessarily want to care about every little detail of the LTE decode and demod. So it's kind of in a way like the FFT block in gunner radio, It provides all the hooks that you need to do the FFT in gunner radio, but if you go and read the source, you find it's just making a call to FFTW in a lot of situations. So that's kind of the approach I took here is I want to be able to throw data at it from gunner radio, and I want it to be able to do the decode and demod just down to the MIB, the master information block, and tell me what did it find. So this is the cell that's just down the road, 236, Verizon downlink at 751. And right now you're probably wondering, I'll hit this off because I know I'll get a question about it. Did you look at GRLTE or OpenLTE or other solutions like that? And yes, I definitely did. I took a lot of time looking at those. One of the things I think that you have to come to terms with when you're going to use something open source is how active is it and how much effort do I want to put into it if I find some issues with it. So I actually love GRLTE. I think it's an amazing project, and I like so much I even tried to read the thesis in German. I don't speak German, but I tried to read that, and it's an amazing project. But for me, I wanted the maximum effect with the minimum amount of lines of code that I have to maintain. And so, kind of surprisingly, I think, for anybody who's familiar with out-of-tree modules and stuff, once you skim the header files and all that kind of C++ boilerplate, this boils down to about 300 or 400 lines of actual logic to just pull in the frames and make the function calls, the library calls for SRS LTE, and do the stuff I want to do with it. So that's really why I went with that. That's what it looks like. It's pretty darn boring, actually. So the only prerequisite is that you sample the input at 1.92. It's a nice normal LTE input rate. So RTLSDR works just fine as is, no resampling. Most USRPs, Blade RF, and for anything else, just put a resampling block in front of it. Get out of that. Works great. LTE Trigger is a hierarchical block. And inside of that, it looks like this is a little bit of simplification, but there are basically just 3 blocks. One to do primary synchronization, secondary synchronization, and the master information block, Decode. And so PSS kind of does the Zadoff-Chu type of correlation stuff. And once the frame correlates well, and you can set that correlation threshold, it passes down. And if it successfully unpacks the MIB, that's considered the cell is detected. And so it would send a asynchronous message that's tracked, and that I think it's a PMT dictionary type of thing. It just includes the cell parameters that it was able to detect. And then I have a little interface to that to just kind of pull that information out of it. So I'm feeling a bit saucy right now. I think I'm just going to try to demo something like that. So give me. Okay. So this is not going to. I'm not going to do it with the RTLSDR. That's a little too scary for me. But so the idea is that I've got a frame of LTE data, and I've got some noise, and I'm going to add them together, and then I'm going to throw that into the LTE block. That's all it is, some noise and a synthesized frame of LTE. You only need 1 frame for LTE to do the memo unpack because it's repeated every frame. So let's see if this actually works. Oh, it works over here. So, as I said, you've got the synthesized downlink signal and some noise, and doing a little SNR calculation there, and obviously, is able to pick out the cell ID, which, if you look up at the file source, it's a 6 PRB, 6 physical resource block, and ID 123. So it's actually pulling out the stuff that is designed to do, which is nice. And it works pretty decently. So in my title, I said that we want to detect at low SNRN. I don't mean that we're trying to push the boundaries of what you can do, with decoding and stuff. But I mean, if we didn't have this real-time analysis block on the IQ and we only were sending the power data, we would basically be relying on threshold, a power threshold to see if there's something in band. But with this in front, we can drop this down. So yeah, you can see it lose tracking and pick up tracking and stuff. But it will pretty happily track it like -10, and you can kind of lower the threshold here. And it'll pretty happily track down in this region like that, like -10 dB. And that's kind of what I mean is this gives us a benefit over just relying on some kind of a threshold detection from the power data. This can detect some cell parameters, detect the signal, and send an event up and say, hey, we've detected this signal in band. So that is kind of that. So let me bring this back here. And I'll Okay. So I'll just go ahead and wrap up here then. So that's it. I just mentioned some of the stuff that we're working on at ITS, how we're using open source software gunner radio and some lower cost sensors to try to affect spectrum sharing change in the near future. And then lastly, I introduced GRLT Trigger, which is open source on GitHub. It's github.com/ntia/GRLT Trigger. I had that on my last slide, but I don't want to scroll through. So with that, I'll wrap up and let you guys ask any questions.
Yeah, so we have a couple minutes. Oh, Michelle. Didn't even get a chance to ask for questions.
Hi, I'm a little alarmed by something. I hope you can help me out. It looks like the measurement scheme is set up really well for primary users where you know what the modulation scheme is. For bands where you have secondary users and modulation is dissimilar, how are you accounting for that usage? And my agenda here is because I'm interested in lots of bands where I am a secondary user. It looks like I'm just going to look like noise, and I'm not going to show up in your scheme. It's going to look like I'm not utilizing my bands, and I'm going to get eliminated from policy discussions unless I can afford a lot more lobbyists. So how are you going to account for that?
Yeah, so actually what we're using this kind of thing for is to protect the incumbent. So we would want to see if anybody is coming in. And so, for example, in like the NOAA satellite type of thing, downlink, is anybody, that's a bad example because that's actually the uplink, but we would want to see, is there any noise, is there any LTE in band that could interfere with that? And one of the reasons that we're working on this specifically is because that's one of the things they're worried about. So they've asked us to look, in the case of NOAA, at LTE in-band interference at -10 dB SNR. That's a specific requirement for them. So that's one of the reasons that we're looking at this specifically.
Okay, maybe follow up afterwards. Yeah. Okay, thank you. Tom?
Well, I do want to actually, it follows on a little bit. I think I'm taking a different aspect than Michelle was. So one of the, we're a group of makers. So that's when we kind of come to it from building new things, and we always want to look at the next cool thing and the next use of this stuff. Mm-hmm. And you're right, the regulators and the FCC are very pro spectrum sharing. Like, they really are pushing in that direction, but they have to be, you know, this goes back to what you said. They have to be cautious about the primary users, the incumbents that are out there. I think one of the things that maybe is lost on some of us in this field of, we know we can do a lot better if we have this dynamic spectrum sharing, and everybody gets to choose their spectrum based on their, you know, their needs, desires, the rest of the environment. And another part of that is we're now indoctrinated with this idea. Like, I was going to pull out my phone to show, like, I buy a new phone every year because it's just this kind of throwaway technology. I can't do that because I actually don't really know where my phone is right now. I just left it somewhere because it doesn't really matter that much. These are tossed, these are throwaway things. But it's true. So we have this idea that technology is actually, so every year I get a better piece of technology. The incumbents don't have that luxury. You know, the 3.5 gigahertz radars that you pointed out at the beginning of your talk, those are 40-year-old radars, and they're supposed to last at least another 40 years. That's a huge upgrade cycle. I wonder if, and coming from NTIA, I think it's a perfect organization to start maybe addressing these questions, getting us some understanding of the number of incumbents, how much they affect the population, what the cost of upgradability might actually be, just to give us some idea of how we have to actually approach this carefully while still also having really good ideas and trying to push technology forward.
Yeah, it's a great plan. I think one of the cool things about working for Department of Commerce is that we are actually, trying to do this kind of research to try to open the spectrum to new uses and stuff. So we're kind of a voice in the government to be able to try to get new technologies in. So it's definitely the kind of thing that we're interested in. Not me, I'm just an intern, but that there are people listening that care about that stuff.
All right, we're out of time. I was hoping to abuse my mic privileges and actually ask you how this could be leveraged for DARPA's Spectrum Collaboration Challenge in terms of detecting incumbents. But we'll have to have a discussion later. Let's thank our speaker. Thank you very much, Doug.
Thanks.
So